Okay, so welcome everyone. So we will try to wrap up the diffusion model topic today. So I will do a brief review of what we have done so far. Um, so we started with, um, so this is a review. So we started with uh, a latent variable model, which is like this, and this is used in VAE. And we thought about computing the marginal width P from the joint, and we also know that Px is given by this using the chain rule of probability. And then we looked for the evidence lower bound, or it is called elbow. And then when we look at that, then we found that this is lower bounded by by this quantity. So we applied Jensen's inequality and so on, and we also introduced an importance sampling Q5, and with this we had this evidence lower bound. And if there's also another view where we have seen that this is this is equal to expectation of Q phi z given x log of P x z divided by Q phi z given x plus the KL of Q phi z given x P of z given x. So we also have this equivalence, and from there we could see that in fact minimizing the KL divergence, this one is a good thing. So then we if we look into this, so in the VAE we have expectation of Q phi z given x log of P x z divided by Q phi z given x, and this is so basically we solve for this from here. Then we have that this is expectation of Q phi z given x log of P theta x given z and minus d KL of Q phi z given x pz. So when we solve from this, then we have these terms like this is a reconstruction term, and this we call it a prior matching. So we have these two terms for the VAE. We have reconstruction term and prior matching term, and we choose Q phi and P to be normal. So Q phi z given x was normal mu phi x sigma phi square x I, and P z was normal z0 I. So these were the assumptions that we made. So we had the x, and we went to the latent variable z, and then we reconstructed the x hat. So the reconstruction term is when z is given, you're supposed to retrieve the x, and pz is the probability distribution for this, the latent variable. And what we are saying with the prior matching term is I get a z from x, so pz given x, so this pz given x, and then we are comparing with this using KL divergence. So KL divergence we use to compare densities. So here we compare with that in the VAE. So that's the second term here, that is prior matching term. And in diffusion model, what we did is that we generalized this idea. Okay, we said that let us do this multiple times. Okay, so then, and there were few details here that we used so-called reparameterized centric and so on. So those were the details there. And so from here, if we build on this idea recursively, then we get to so-called variational diffusion model. So then the next step is hierarchical variational autoencoder. So we are trying to kind of do a quick review of what we have done. We have done like four classes. So we're trying to kind of make a good map of what we have done. So then we went to something called hierarchical VAE. Okay, so this generalizes VAE. Okay, and basically extends to multiple hierarchies. So, and latent variables are interpreted as generated from higher latents. Okay, so the latent variables are interpreted as generated from higher latent. Okay, so basically the picture that we have in mind is to extend from VAE, we are imagining something like this. Okay, so now in place of one latent, I have multiple latents, so on. Okay, so this is the hierarchical VAE. Then we did a further assumption is, since now we have a chain, we want to define a dependency. So what kind of dependency I want, right? So in a chain, do I want, if I'm here Z2, do I want that it only depends on Z1 or it also depends on X? If I'm at Z3, should I say that Z3 is dependent on Z2, Z1 and X? Okay, so in a sequence, what kind of dependencies we want? Do we want like this also? So this was the decision that we made, and this was, let us say, idea number 2, let's say. Idea number 1 was think of VAE as a hierarchical approach, but then the next idea is that in the hierarchy, what are the dependencies? Okay, so this is kind of idea number 1, think of hierarchical approach. Okay, then idea number 2. So today we will also see everything in this view. Okay, how the ideas were organized. Okay, just to wrap up. So idea number 2 was, how do you define these dependencies? How to define dependencies in this hierarchy. Okay, so this was a decision that we had to make, that what kind of hierarchy. Then we said, let us go for the Markov chain. Okay, so Markov chain. So this is now like a chain, and the Markov chain is when only dependency is the previous one, just the previous one. So Markov chain says just look at dependencies like this, okay, like a chain. Okay, and so basically it simplifies for sure. Okay, if I assume dependencies, multiple dependencies, like x1 is also responsible for x3, okay, x2 is responsible for x3, then computations will be very difficult. Okay, in fact, that's the reason, because having multiple dependencies seems to be a good idea. That why not, right? Let us make the third step depend on all the previous step. Okay, but from computation point of view, you have to make decisions what kind of models you want. Okay, so this will simplify. It's a simple hierarchy. So that was the idea number 2, and with the notation of the hierarchical VAE, then we can write this as x1. So let us say this is our latent Z1, Z2, and Zt. Then with our notations, we say that the forward is Q, Z1 given X1, and then this is Q Z2 given Z1, and so on. And then this is Q ZT given ZT minus 1. Okay. So these are just the notations that we carry over from the VAE. So this is now the forward process, and then we can define the backward process. So in the VAE, if you want to make this in terms of VAE, then this is like this. Okay, for the VAE. So there is a forward process and there is a backward process. There is an encoding process and there is a decoding process. Okay. So forward process is like encoding and backward process is like decoding. So we extend those notations. Okay. So when we go here, we say what is Z given X. When we go here, we say what is X given Z. Okay. So the same ideas now. So we will say, so let us say P here. So what is X1 given Z1? Now what is Z1 given Z2, and so on. What is ZT minus 1 given ZT? So this is just a notation of idea number 2, where we just carry over the notations from the VAE. So then the elbow bound that we had for VAE, okay. So how will it extend to the hierarchical VAE? Okay. So that was the next step. So once we define a graphical model like this, okay, where let us say I'm looking only at the forward. So this is like a graphical model here, a DAG, and then I would like to compute the joint probabilities. Okay, so I mean I want to get one of these from the joint. Okay, so that's what we did in the case of VAE. In VAE, we said that I want to estimate the probability distribution this, but then I want to do it from the joint. Okay, so then we said that okay, marginalize this. Okay, so we said that we will marginalize. We will take the joint, all the variables you have in your model, and then marginalize over all those that you don't want. Now the same idea will be repeated here. In the model, I have all these variables, and then what I'm really interested in is Px. I want to take all the variables in the model because that's part of my design, right? That's how I think about my problem, that I want to make use of this. So then we write the joint and same step, and then we find a lower bound of this elbow bound, right? So this is how the variational inference techniques work. Okay, they find some kind of a lower bound. Okay, the original one is not tractable, and hence we will introduce something called importance sampling and things like that to make it tractable. So the next step is follow the derive the variance lower bound. So if we do that, then we have done these derivations before. So in this case, we will have P x z 1 to t is probability of zt. That's a simplified notation here, and P theta zt minus 1 zt t equals 2 to t. So I've just taken out two of the terms from here just to make this notations simpler, and then I can also define the other joint terms. So here I have q phi of z1 given x, and then product 2 to t q phi zt given zt minus 1. So with these notations, we had the evidence lower bound, which we will write it as expectation of q phi x 1 to t x, and this is log of p zt x given z1, and t equals to 2 to t p theta zt minus 1 zt, and divided by q phi z1 given x. So this guy, if you recall, it's the importance sampling step. So these, I won't call them idea for SS, because whenever I do not specific to diffusion models, okay, so importance sampling can be done in for many cases. You do this as a usual step. So in the evidence lower bound, I will ask you to kind of at this step, you look at the derivations. I will provide this links later on. So this step we derived before, and we introduced the evidence, the importance sampling step, Jensen's inequality, and all those, and that makes this. So we are not doing those detailed derivations right now. So t equals to 2 to t q phi zt minus 1. Okay, so this is the derivations that we did. Okay, so we are going to skip obviously. So this is the lower bound that we have. So this is one approach where the latent variables are z1, z2, zt, and the recent variational diffusion models, they said that keep the latent dimensions as same as the original. Okay, so all the Jedi's have the same dimension, but this was not true for VAE. VAE we had this, but then had a smaller latent dimension here. Okay, but here we are saying that let us keep these Jedi's same dimension as x, and we did a notational change that then we said that if the dimensions are going to be same, then keep this Jedi's also as use the notation x also for the Z. So that was just a notation change, I would say. So so one of the ideas proposed was keep the latent dimension same as, let us say, the input x, okay, or let us say x naught is the real image, let us say, then we keep these Jedi same. Okay, so and then with this notation changes, what we have is yeah, so we did a derivation on all of this with this setup where we had this, and we did a splitting of this. So basically I replaced Z by x, okay, and then make the logs split, okay, and if we do that, then we get a we get 3 terms basically. So what we get is log px, and we get expectation of q x1 x naught, log of p theta x naught x1, and then minus of expectation of x t minus 1 x naught dkl q xt given xt minus 1 p xt. Okay, and then we had the final term, which is the sum term, expectation of q xt minus 1 xt plus 1 x naught, and dkl q xt given xt xt plus 1, and p theta xt given xt plus 1. Okay, so we did these derivations before. I'm not doing those derivations, just writing the main things. So we had this evidence lower bound. So we went to hierarchical VAE. Then hierarchical VAE, we said that all the written dimensions are the same. Change the Z to X, and we did this derivation elbow bound. In the elbow bound, then when we split this, then it becomes this. Okay, and then we have these terms that are named as like a reconstruction term and so on. This is our prior matching term, and this is our consistency term. So we have done all this. So the main thing that you will notice was this term, okay, computing this. So this is where we spent quite some time, where we, yeah, I did. One of them was t minus 1, right? That's the mistake, t minus 1. Okay, so this is the consistency term, xt minus 1, xt plus 1, was to introduce the reference x naught, okay, which is the original image. So our focus is this guy. Okay, so basically we want to bring in some ground truth reference for which we will learn p theta. Okay, the p theta here is here, and this is here. So, and we will transform this in a way that basically the scale divergence could be computed. Okay, so a main trick that we did is why not introduce the original image also. Okay, and so what we did is we did the base rule. We changed xt minus 1 let's check the notation is absolutely correct. So xt minus 1, and we flipped it. We had xt minus 1 xt form. Okay, so the later bound is, yeah, so both became xt minus 1 xt, and then the p theta also became xt minus 1 xt. So that became the kind of the backward this process, and this q xt minus 1 xt, we go from here and we derive this later on. So these bounds change to this, and then this p theta, the denoising process that I want to learn, right? So this is xt minus 1 xt. This is the next step we do. Okay, this terms change to qxt minus 1 xt and p theta st minus 1 xt. Okay, so what we do is that what we have in mind is that when we do denoising process, it will help if I have a knowledge of what is the reference image I have in mind that I want to recreate. Okay, so I'm doing this denoising process, but I want to know, okay, where I what is it that I'm trying to achieve, right, after doing this denoising edge step. So this was a important idea where we said that let us put x naught also, okay, as a condition. Whatever we are doing, let us put x naught also there, whether it's forward, backward, okay, because that is there in my hand, right? Why should I lose that information? So that was done as a, so I it may be a little bit I'm doing this with my how I view things. Okay, so I believe that this was a key idea where we put a reference, and we can put a reference because at the end of the day this is a Markov process. And okay, so later here I have to say things like that we assumed Markov process because we thought it makes our life easier, and introducing an x naught does not violate that Markov process, but it does help. It does help if I see the original image. Okay, so that's what I'm trying to say here, that I am allowed to put x naught here. I'm allowed to put x naught here. My model remains Markov, but I know from computation point of view, knowing x naught helps. Okay, so this is what was done later on, where we said that let us write this q of xt minus 1 as q of xt minus 1 x naught. Okay, you see this? We added this x naught, and later on this helps. Okay, the intuition here is that knowing your original image helps. Further down the line you are at th step and so on, this helps. So this is the main idea where you put this additional x naught there, and we are still saying it's equal because it's a Markov. The Markov says that t depends only on t minus 1. So here x naught I'm allowed to put x naught, or even other previous terms I'm allowed to do, allowed to add here. Okay, because Markov only depends on t minus 1, immediate previous one. So this was a key step, and we use this and we derived another lower bound, okay, with this new changes. So let us write down that new one. So what we did as a next step is we derived another. So obviously I'm skipping the derivations. Okay, so today, like obviously I'm not going to tell you how, but we did this already. It's just a review going on. So with this new, what we also wanted was a reference, the reference for denoising. So then we wanted to flip this for the lower bound. So we use a base rule. So the base rule is a way to flip, right? But it will bring its own things. So here what we use as a next step is xt minus 1, and we included this x naught, and this is xt minus 1 xt x naught q xt x naught divided by q xt minus 1 x naught, and we put this in the we do these calculations again with this q basically we replace q by this new term. So then the new elbow bound is like this. So log px is greater than or equal to these are similar things, so I don't have to say again and again. So you see this this changes happened. Okay, we did some few things there. Like if you see, there was expectation with respect to this, but then it changed to this. Okay, and our argument was that computing expectation with the joint can lead to more variance. So let us change this in a way that it splits into. So by this change, we arrive here. Okay, and we got to an expectation which is with one variable. That's one thing, and with this we have this formulation here, where this is the learning process, denoising process, and this is the we say it's a ground truth that we want to compare with. Okay, and but obviously by this process, I mean the intuition behind this is that what we know is what was added as a forward process, because this is something we know, right? What did I do at t minus 1? What did I do at t minus 1 to get to t? And denoising is like, now you are at xt, what will you do to go back to xt minus 1? Okay, so interestingly, we after doing this conditional line changes and then having this joint into single expectation, we flipped it again. Okay, so there was like these two steps which could be a little bit interesting, because first we introduced x naught and then we did these changes, and then later we say that okay, to compute this we again use the base rule, but then we flip it again. Okay, so if we flip it again, then what will happen is that xt minus 1 will be known, because that's the noise that I added to get to xt from xt minus 1. Okay, so these are these tricky places where we do this. So what we did after this is that, so we have this, and then we now we are saying that okay, this is looking like a denoising, so how will I compute this again? So I will say okay, again apply base rule and I flip it, because the flipped variant I know. Okay, so these are the steps. So then the next step is when, so this is the lower bound, so yeah, everything the same. So then let us go to the next step. So then in the next step we say that now to compute this t minus 1 xt, I'm going to use the base rule again to flip it. Okay, and everything else remains the same. Okay, and we flip it, and then what we say as a next step is that to compute this ground truth, right, the reference or the ground truth, what we have a knowledge of is the noising process. So then we write q xt minus 1 xt. Okay, so going from here to here, we achieved we did two things, like we introduced x naught and so on. We broke this expectation computation on the joint to the single. This is the achievement we have. Okay, you may say, why are you going back and forth, right? Why you originally had this xt minus 1, why did you go back and forth? So back and forth is to make these also easier. Okay, so these were the key steps. It looks like cyclic but not. Okay, so we have this is something new here, and we our original goal that we will keep a reference of x naught is intact. Okay, so this means that we apply the base rule again, and this means q, so it flips xt minus 1 x naught q xt minus 1 given x naught divided by q xt x naught. Okay, that elbow lower bound simplifies to this. Specifically the expectation term becomes interesting, low variance, and then x naught is intact. Now these x naught that we brought here, it will help us. Okay, having a reference to original image, that helps us, so that if we do this further calculations with this, we put it there again. But the problem is now what it is actually, right? So this is this, but then a lot of calculation have. In fact, we spent a whole class just to know this. Okay, so then we saw even if I say in advance that these are normal distributions, but then what are the forms of this, right? We assume that this is a normal distribution, this is a normal distribution, but what exactly it is? Normal distribution with what? Mean and variance, right? And normal distribution is defined if I provide a mean and variance. So then we did a lot of calculation on this, and then we found the mean and the variance, which was a little bit complicated, but we could figure out. And then later on, once we had those template for mean and the normal and normal here, there is a closed form solution for computing KL divergence for two normal distributions. So those were the so here if we So so what we know already is that this guy, which is the next noisy image from the previous one, from the current one I mean. So this is a normal distribution. So that's something we assume obviously. So we inject a noise each time to get to another noisy and so on. And that is kind of deterministic, because I know in advance how will I change my mean and variance so that I get to the next one. So for this, the q xt minus 1 x naught is, so due to Markov, when I feel it is good, I drop it. Okay, when I feel it's necessary, I keep it. Okay, that's the point here. So this is like normal xt and square root of alpha t xt 1 minus alpha t identity. So this is something we have assumed in the forward process. Okay, that's our assumptions in the forward process, that it will be a normal distribution, and xt given xt minus 1 is given with this mean and variance for the normal distribution. Okay, so this is something that is known. And later on, if you remember in the previous classes, we said that I know that I'm creating a noisy image at each time, but then what is the way to change this mean and variance? Okay, so that's called a noise scheduling, right? So we looked into this. So noise scheduling is a process where you schedule how your noises are going to be injected here. So meaning, how will you choose alpha? Okay, what is your choice of alpha at each time t? So that's something we have to think, because at the end we have to get to some qt which should be standard normal. Okay, so if you inject noises arbitrarily way, there is no guarantee that you will get to standard normal. Okay, so this is a noise scheduling process, and it could be done in many ways. In fact, one of the research points could be this only. Okay, what are the ways you propose to do this noise scheduling? Okay, so people can come up with variants. In fact, people are trying this. Okay, what are the good ways to do this? So noise scheduling is one possibility, and we looked at SNR, okay, signal to noise ratio, and so on. So there is one paper which proposed some interesting noise scheduling, but we will come to that later. So this is the q xt given xt minus 1, and we believe we have that this is normal. But what I'm not telling is what were our choices alpha t. That is a separate another topic we will deal. That is another ingredient or key idea that we need. Okay, so for the moment we see that xt given xt minus 1 is normal. Okay, so then so with this what we have is so then we said that we can use the reparameterization trick to say that xt minus 1, how this is obtained from how this is obtained as a next step. Okay, so here, and what we are asking for is my q xt given xt minus 1 is a normal distribution with mean and variance like this. But then I can also see this as being generated like this. So this is indeed a sample with mean and variance square root of alpha t and 1 minus alpha t. So if you calculate the mean and variance of this, it will exactly give you what you have asked for in the template that you have. Okay, so this is the so-called reparameterization trick, where I generate the normal distributions with a proper scaling and translation of mean and making use of the standard normal. So similarly, xt minus 1 can be done, and then with this, and the idea behind doing this was how do I see xt, right? Because if I see xt, then it's given in terms of xt minus 1, which is also not known, right? So the idea is that if I see xt from the view of reparameterization trick, because from xt minus 1, how do I go to xt? So this is how I go. Then these are still unknown. So what I want to do is that I want to see in absolute terms what xt is, not in terms of xt minus 1. So basically I will do this recursion in place of xt minus 1. Again, it will be square root of alpha t minus 1, xt minus 2, and so on. So if you apply this recursion, then everything will go until x naught. So xt can be seen in terms of x naught, and x naught is the real data that you exactly know, right? So then by doing this, we can say that this is square root of alpha bar t So basically this gets multiplied due to recursion. So then this multiplication of all the alpha t until t is denoted like alpha bar t. So x naught and 1 minus alpha bar t. Okay. So rather than saying that this is the one, this looks like this. Now we are explicitly saying that xt is sampled from normal distributions where everything is there. Okay. So with but I mean with reference to x naught, which is the real data that I know with respect to that how to sample xt, given alpha t is known obviously. Okay. So alpha t is still unknown. That is part of upcoming discussions we will do. But this is what xt is, and then remember that our whole focus is here, and we are trying to understand this, which we wrote there. Okay. And so with this, the mean for mu xt will be, so we write this as, and same for t minus 1. Okay. Because we need for, so yeah, t minus 1 I want to flip, right? And yeah, basically I want to substitute with this, right? So then we looked into this, and right, so that's fine. So then so for these samples, then we are asking for what would be the mean and the variance in reference to x naught, I believe, right? Okay. So mu xt mu. Okay, this was a long derivation. Okay, now I remember, because I was thinking. So basically, as a last step, I'm writing directly this. Okay, and this was a long derivation we did. Basically, we computed this, and then we did a lot of calculations, and then finally, what we said is that this will now this will then look like. So this will then look like qxt minus 1 xt x naught, and this looks like a normal distribution xt minus 1 mu q xt x naught sigma qt. So we did a lot of calculations after this. Okay, and basically we substituted all this normal distributions, and then finally we figured out that this is also a normal distribution with mean mu and variance sigma q. So mean mu q xt x naught was square root of alpha t 1 minus alpha bar t minus 1. Yeah, this is xt, and then plus square root of alpha bar t minus 1 minus alpha t x naught, and then 1 minus alpha bar t, and then right, and with those we also had, so I wrote this normal distribution, and then we also know what is a normal distribution for this. Okay, and then we also know normal distributions for this. So all these derivations were done, and then we put this together and then try to figure out what exactly this looks like. So then it looks like this mu q and sigma q, and where sigma q t is 1 minus alpha t and 1 minus alpha bar t minus 1 by 1 minus alpha bar t. Okay, so this was the step that we did, and then the next step was we did the KL divergence comparisons. Okay, so we derived what is this, and then we know the template for this as well. Okay, and then we say that, okay, what is the closed form solution of KL divergence? So then in fact, if we go and minimize this, then what we did, what we got in the end was, so you can do it here. Okay, so I'm missing like few derivations obviously, because I just want to show you the top level view of what has been done so far. So then we went ahead and say, okay, let us look into the minimization of this, because we do want to minimize this, because the learning to predict the denoise image, right? So that's the process here going on. So this distance has to be minimized. If it minimizes, then this would mean that p theta, the learning process has learned things correctly. Okay, so it has learned how to denoise. Okay, so hence we will minimize this. So then we went ahead and did a KL, minimize the KL divergence. So when we minimize this, again there is a derivation here. So we are and when we derive this, then we found that this is argument of theta 2 sigma q squared and mu theta mu q squared. Okay, and so we had here, and then we also had a knowledge of mu q, okay, which was computed for this guy. So that's in the previous one we explicitly said what was this normal distributions with mean. So that mu q is known, and then we wanted to know like what could be mu theta, right? What would be the mean of the learning process, right? The denoising process. So then, so here we had mu q, which was alpha t 1 minus alpha bar t minus 1 xt plus square root of alpha bar t minus 1 minus alpha t x naught, and then divided by 1 minus alpha bar t. So looking at this, because we want to kind of we want to understand what could be the template for this normal distribution, right? So to do that, we are looking at this guy, and we are thinking what, looking at the mean and the variance of this guy, what could be the correct choice for this guy? Okay, so if we look into this is the ground truth, right? So we call this guy as a ground truth. So then when we look here, then we say that okay, what is our objective? Our objective is to predict the real image x naught. So why not do a prediction of x naught here? Okay, so then we put something called x theta. X theta will be a predictor of x naught. So then mu theta we define is everything same, just the last one x naught will be now will be a prediction problem. Okay, so then it will be square root of alpha t 1 minus alpha bar t minus 1 xt alpha bar t minus 1 alpha t, and this is x theta hat xt t divided by 1 minus alpha bar t. And in the derivation that we did here, we assumed here that the variances are same. So that's why the variance term got cancelled when you took the KL divergence. Okay, that the variance is same. Okay, so this was also, I would say, a key idea here. Okay, that you wanted the variance to be same, so that gets cancelled. So hence you only have the difference of the mean. Basically, you want to learn the mean of the denoising process. Okay, so then explicit expressions for the mu is known, and then you are thinking, okay, what should be my prediction of the mu q? So given I am at xt, what should I do to predict the denoising process as a to go to xt minus 1? Okay, so this x naught that we kept is now playing a role here. Okay, this x naught is now showing up, and this x naught is the reference that I'm using to say that okay, make the predictor like this. Obviously my goal is to retrieve x naught, so why not do a prediction for that? Okay, so why not change my mean in a way that I am learning to predict x naught? Okay, so with this choice of the mu q and mu theta, if we put these things there, then ultimately things boil down to because everything gets cancelled, because this guy everything gets cancelled, right? These constants are the same, so ultimately the difference between mu theta mu q is just x hat and x naught. Okay, so this means that having such choices indeed means that I'm learning to predict the original image. Okay, so there is a lot going on in these things, right? Derivation. So that's why I had to do this review to kind of connect things from the top level. Okay, sometimes we get lost in derivations. So then this, okay, the key idea was variance keep same. Then you get to this, and then you said, okay, what is the mu theta? Then you looked at the original image. Then you said, okay, that's my plan to do that. And then now if I look into this argmin, then it boils down to, so basically argmin came from the KL. So I will write the KL theta dkl and q xt minus 1 xt x naught p theta xt minus 1 xt. So we rewrote this, and then we know that it was mu theta minus mu q. So ultimately, obviously, like we did all these derivations, and then in the end, what we get is 1/2 sigma q square alpha bar t minus 1 minus alpha t square divided by 1 minus alpha bar t squared. Then as I said, like those things come out, and then x hat theta xtt minus x naught. Okay, so this tells us that VDM, the variational diffusion model, all this is what we're doing, boils down to learning a neural network to predict the original ground truth image, the original okay. So all the ideas like putting x naught original image in the conditional, all this is playing a role here. Okay, this is giving you a reference. Okay, this is the prediction I'm supposed to do, and so everything fits perfectly. Now now what we want to understand is what are the choices of this alpha, right? Because I am injecting a noise each time, but what are the good ways to do that? So the next set of ideas, I will call this idea 5, is noise scheduling. Okay, so and that is related to signal to noise ratio and things like that. Okay, the paper by Kingma and so on. All these are recent paper. What we're doing is last 3 years work. Okay, just everything we are doing is last 3 years work, 19, 20, 21, 22 also. Okay, let's say 4 years. Okay, these are like 2021 paper. So so before I go ahead, so this was one of the terms in the evidence lower bound. If you recall, there was a summation, and this summation was going from t equals to 1 to capital T. Okay, so basically we have to take an average of this. So sum is kind of average, right? So what we can do is take a expectation over t. Okay, so there was a sum, and then we can change this to something like argmin theta expectation of t. Let us say this sum was from 2 to t. So let us say this choice of t is like uniform, let's say. Okay, I want to do this sum as an expectation, and when I compute an expectation, then the question is this is expectation over which distribution. Then I'm saying it's a uniform distribution. I will pick t uniformly. Okay, while I'm computing the sum. So this is expectation of q xt x naught, and the terms xt minus 1 xt x naught and p theta xt minus 1 xt. Okay, so basically this is what we are supposed to do. Okay, so I will write an algorithm also, but so coming back to what are the choices of these alpha, right? So that's called learning noise parameters. So then we basically looked into this, and then what we found out is that this whole term could be written as follows. So this is equal to half of, so all these derivations we did. Okay, you can check the previous. So t minus 1 minus alpha bar t by 1 minus alpha bar t, and norm of x hat theta xtt minus x naught. So basically you don't have to focus in this term, it's the same. We just did changes to these constant terms that we had. Okay, so all these derivations you can have a look. Okay, so this could be written as the difference of these two guys. Okay, now this ratio is of mean and the variance is signal to noise ratio. Okay, so then this is SNR. Okay, so this is the variance and this is the mean. So SNR is usually defined. So people who work with this signals and so on, right? So they use this a lot. This is defined like this: mean squared by variance. Okay, so in our case, mean was actually square root of alpha t minus alpha t. So when we square it, this becomes alpha t now. So basically, we are having a difference of these these SNRs. Okay, so this can be written as half of SNR t minus 1 minus SNR of t, and then x hat theta minus x naught. Okay, so this was the view taken by Kingma in, I believe, 2021 or 2022 paper, I think. So this will help. In, so how will it help, right? If I define so-called signal to noise ratio, how does it help in the in scheduling these alpha? Okay, so the idea here is that since I'm doing a forward process and my ultimate goal is to get to normal with zero mean and variance this, then it seems like it's a good idea that these SNRs go to zero. Okay, basically the mean should definitely go to zero, right? So this is the idea that if I am planning to make a scheduling of this, then from the view of signal to noise ratio, what I want is that this SNR goes to zero. Okay, so if SNR goes to zero, then can we think of this as a prediction problem, right? So from here to here, it kind of like not prediction, let's say some function that goes to zero, right? So then we looked at and it goes to zero kind of exponentially, not the drastically one, okay? Because then it will not learn, okay? So if you do it in one step, it won't learn. And basically it will try to, one step will be VAE, right? But that's something we don't want to do. Okay, so we are having exponential like this that decreases. So this is our exponential. So from here we looked into the exponential, and then we said, okay, what is the function that will make it gradually decrease? Then we said, let us use an exponential. So then the correct form was SNRT was SNRT is a asymptotically decaying function which is exponential of minus omega eta t, where omega eta t is some monotonic increasing function. Okay, monotonic with t, so that the overall exponential of omega nt will be decreasing. Okay, so that was the, so from there we can solve for alpha bar t, which will be so we can also so SNR is this, so alpha bar by 1 minus alpha bar t becomes a sigmoid. Okay, so sigmoid function, if you can see, okay, so 1 by 1 plus e to the minus x is the sigmoid, right? So this becomes a sigmoid omega nt. So this is a way of kind of doing a scheduling. Okay, here obviously like yeah, eta has to be learned. Okay, so again it could be taken as a neural network here. Okay, so we will take omega nt as some kind of a neural network which is increasing in time, and then alpha bar t is sigmoid of that. And if we do this, then we will have to change our optimization problem overall with eta also. Okay, so then we will have to do minimize overall, I guess, right? So now we have to optimize over eta as well. So there will be eta as well, because in the scheduling alphas that I have are dependent on omega eta. Okay, so there is the alpha is become also the scheduling process is also a variable with respect to eta, and then overall it becomes optimization over eta theta. Okay, so this is what we have as a final step, where scheduling is also there. Because if there is a scheduler that does not minimize this, then it's a bad one, right? I mean, so ideally I'm looking for a scheduler that that learns to predict the original image. Okay, so overall as a maths, this is like the whole optimization problem. Okay, since I said neural network, if the losses are high, I will tune the parameters of the network. Okay, so I will do gradient descent with eta also. Okay, so if I see that the losses are very high, one gradient descent will happen with theta, another gradient descent will happen with eta. Okay, so basically we are training the neural network to also learn how to schedule. Okay, so that could be done. Okay, but this may contradict with what I said in the beginning, in the very beginning, that we don't make this as a learning process. Okay, so there are papers which did some linear scheduling and so on. Okay, where they just add some, let us say, linear or whatever scheduling you do, right? At the end, they ensure that they go to 0. Okay, but in this paper, signal to noise ratio, they kind of make it learnable also, because now eta is there, so it is also trying to learn how to go from here to here, what is the optimal way to go from here to here, and so on. Okay, so that's the learning the how I inject the noises. Okay, so then we looked at so here what we see here is that here is that we are trying to predict the original image x0, and then we looked at variants of this where instead of predicting the original image, we are predicting the original noise that was injected. Okay, so I will write those expressions. We did all those derivations in the previous classes, so we don't have to obviously do that, but overall we have an overview of what happened in this topic, right? So there are other equivalent interpretations. So another way is that I see x0 as xt minus square root of 1 minus alpha bar t epsilon naught divided by square root of alpha bar t. So the way you see x0 gives you different interpretations. Okay, so the papers that followed try to write x0 in different ways. We will see one more way. Okay, so here this is simple. This is like this is just the reparameterization trick. I knew that xt was square root of alpha bar t plus 1 alpha bar x0 epsilon naught. So from there I thought, okay, what if I choose my x0 like this? Okay, so if I choose my x0 like this, so what will happen there? Okay, because as I said, with this as a template, you can play around with different interpretations of x0, and although mathematically they are equivalent, some of the variants give better results. Okay, because numerically things can be different than what you actually see as a pure maths formulas, right? So this noise prediction was better. Okay, in the recent papers, noise prediction was found to be better compared to that form where you are trying to predict the original image. So with this choice of x0, what we found is that the argmain problem theta dkl q xt minus 1 xt x0 p theta xt minus 1 xt. Now this became argmin of theta 1 by 2 sigma q squared 1 minus alpha t squared divided by 1 minus alpha bar t and alpha t, and then norm of epsilon naught minus epsilon hat theta. Okay, so we did this derivations with this choice of x0 I put there and do the calculations, then I got this. Okay, so this is the difference, epsilon naught minus epsilon bar t, and here you have x0 minus x theta. So now what I'm saying is that it's equivalent to predicting the first noise that I injected, right? So this is the first noise. So x0 was here and x1, so this is the epsilon naught noise that I injected, right? So predicting the first image is like trying to understand what was the first noise that was injected in the forward diffusion process. So this was our second interpretation, and for this we can write an algorithm now. Okay, so what exactly is an algorithm for the diffusion model, right? So I think I've written it somewhere. So algorithm, yeah. So let us write an algorithm for training. Okay, so this is the various diffusion model. So this is the first step. The first step is that you repeat the following steps as a loop, and then you sample x0, and these are the true images, and then you sample the time. So this is uniform. And then the fourth step is take a noisy sample, and then the fifth step is take do gradient descent. So do gradient descent with the with the gradient computed for epsilon minus epsilon theta and square root of alpha bar t x naught plus square root of 1 minus alpha bar t epsilon. Okay, and this is like until converged. So as you can see, after all these derivations and whatnot we have done, the algorithm is very simple. Okay, so to arrive at this algorithm we did all those. Okay, but at the end this is just a 4-line. In fact, the first two are even like okay, it's a for loop statement, and this for loop like is like trying to kind of run this 2, 3, 4, 5 in a loop. Okay, until you are satisfied with the construction and so on. So here, or basically you are minimizing the loss. Okay, here so what it says is that take a sample. So let us say I picked one cat image. Okay, this distribution is not known obviously, but let us say but this data is there for me, right? The samples are given to me, so I can pick one cat image, let's say, and then I will take a t which is uniform from 1 to 2. So I will pick any of the time step out of the t. Okay, and then I will take an epsilon noise parameter that I have. I mean, from the standard normal I use that, and then eventually it boils down to minimizing this, right? So minimizing the top KL divergence term is just minimizing this. Okay, I have not put the eta term, but you can use the eta as well with the scheduling. Okay, but then you will be doing gradient descent also with eta. So there will be grad eta, also minimize the loss over those. Okay, because then when I'm doing minimization for eta, then etas are lying here because the schedulers are with this alpha t. Okay, so those things like we can like introduce here in the algorithm also. So this argument with eta I have not included, but it can be done as do gradient grad eta, not for the epsilon, but now your focus will be here. Okay, so this is a simple simple way to train, right? So you do this steps until the loss function is decreased, and when you have done this process and the loss is minimized, so basically this is your loss. So if your loss is minimized, then you will check in your code what is the value for this, and for different iteration of theta, because theta is getting updated here. Right? By gradient descent we mean that that theta I is updated by theta I minus 1 minus, this is the gradient theta term, the whole term that we have. I put it here and keep getting this theta I under this loop, and there may be a time. So how will you know the method stops? Basically you will look for this norm. So basically the gradient should become flat, right? So for function minimizing, so the gradient should become flat. So basically if this gradients, you take a further norm of the gradient, and the gradient is become 0, then you have arrived at some minima. Okay, we are not going into the optimization, a specific thing right now, whether it will be convex functions or whether there will be unique minima or so on. We are not going to that, but let us hope that there will be unique minima or so on. Then we will go to this minima, and then that's when we will say that that we have learned. So what does that mean? By learning we mean that that basically this theta was the was involved with this, right? So basically we have learned to denoise like this, right? So this is our p theta step by step, right, for different times. So learning theta from this algorithm specifically means that I have learned how to denoise with this optimal theta star. Let us say theta star is the solution for this. Then with that theta star, I have learned how to denoise. Okay, so let us say that you have learned this theta star. Then the next step is obviously after training you want to generate new images, right? So then the next step is sampling, right? So sampling will happen from the standard normal, right? So I will pick a vector from standard normal, and then I will say, okay, let us produce some image. This is real, I mean close to the true data, right? So another algorithm will be the sampling algorithm. After training, sampling. So first step xt. So as usual we take this from our standard normal, and then we do for loop t equals to t1 do and z 0 I, and then xt. So this is our third step. Fourth step is xt minus 1 is 1 by square root of alpha t xt minus 1 minus alpha t alpha bar t epsilon naught xt t plus sigma sigma z, I guess. Yeah, sigma t, I guess, right? So this is sigma t, and for return. Okay, so after I have done this, the hard part is the training part, and then I have started generating these x naught. Okay, so so in this, if you compare with the GANs, right, you will see that there are you have to go through steps. Okay, in GANs you do it in one step via generator, but here you have to go through t time steps. Okay, and hence the sampling with the diffusion models is slow. So go for t steps, hence sampling with diffusion models is slow. Okay, compared to hence GANs still remain very competitive. When I have to generate images very quickly, then this is GANs are better. But in general, let us say if I have to generate very high quality images, then diffusion models are better. Okay, there are some new papers like GigaGAN and so on. They are almost like trying to have the same quality as the diffusion models. So it can happen back and forth. Okay, GAN tech models will come, they will come with improvement, and the diffusion models will improve, and so on. So this may keep happening. GANs are still popular, as I said, because of the very fast sampling. So this is the algorithm for the diffusion models, and obviously with different choices of scheduling, different choices of let us say how you interpret these things, whether I'm trying to predict the original noise epsilon naught, or whether I'm going to predict the x naught. So then your objective will change. So that's also a research area. Okay, what objective we are trying to learn. Okay, so here also variations are happening. Okay, these three ideas that you third idea I will show now, but these two ideas were two different papers. Okay, and then the third idea was based on the score matching, and this score matching idea was derived from the Turis formula. Okay, so all this we have done before. So, but score matching idea became more prominent. Okay, became more useful, you can say. Okay, compared to this. So, in score matching, I won't go through all the derivations. So, score based generative model. So, in this case, remember every time I am trying to see how I can see x naught, right? The first idea was how I see x naught. Well, in the first idea I didn't have anything for x naught, it was just x naught. So then the learning was x zero minus x naught. Then the second we used reparameterization, and see we thought that okay, x naught is seen in terms of xt. We did that, and then epsilon came, and then we had the second interpretation in terms of noise. And then the third idea is based on writing x naught differently. So again I will write x naught now, but we see x naught like this: xt plus 1 minus alpha bar t grad log pxt divided by square root of alpha bar t. This is another way of seeing x naught. Okay, and you have these terms now. Okay, grad log pxt and so on. Okay, so so with this using yeah, I mean I can write few steps, but I want to skip it because I already did it. So what I want to say is that with this, like we derived this in the last class. Okay, so you can check how did I derive this. This was using Turis formula, so on. But then I mean so from here what we got is mu q xt x naught was 1 by square root of alpha t xt plus 1 minus alpha t by square root of alpha t grad log p xt. So we had this mu q, all these derivations we did, and then we said that this is our mu q, which is the reference, then what could be our learned mean? So then we said that mu theta. Okay, this part you see in the videos. Okay, there seems to be a jump like why is this? Okay, so we did this before, and then we said that mu theta xt is 1 by square root of alpha t xt plus 1 minus alpha t square root of alpha t s theta xtt. So by looking at this reference mu q, we said that like before we said that why not match this log p with this s theta function. Okay, so why not try to predict this gradient of the log of the density, required density. Okay, so this is called score based functions, where when you take the gradient of the log, then this is called score. Okay, that's the name score. So then we are saying that let us try to learn the score by taking a difference of this. So then if we take a difference, if we do the argmin like we did before, then in this case it looks so over theta, then q xt minus 1 xt x naught and p theta xt minus 1 xt, and this became argmin theta 1 by 2 sigma q squared 1 minus alpha t squared by alpha t, and this became, yeah, so s theta minus grad log p xt. Okay, so previously we had x theta minus x naught, then we had epsilon theta minus epsilon, and now we have s theta minus grad log p xt. So this is another view where we are trying to learn via so-called score matching. Okay, so when we looked into this, then in the score matching, then the question was how are you going to minimize this? Yes, again it's a problem of optimization, like how I'm going to minimize this. There is this s theta and then log and so on. So s theta is, I have not defined, right? So s theta is grad log of p theta, the density that I want to learn, and the density that is a reference. Okay, so we are supposed to minimize this term. So then we looked into, in the last class we looked at what are the feasible ways to do this. Okay, so then to see this, what we had what we have seen in the last class is we spent some time on this. So I will just write down the main results of what we did in this so-called score matching type ideas. So what we proved in the last class is that argmin theta and expectation of half of s theta x minus grad x log of px. So what we found, what we see if we look into this is that it is impossible to optimize on this. It is impossible because I don't know px, the true distribution, anyway, right? So in this idea, this was troublesome. So then they changed this argument to something that is tractable, and we proved this in the last class, that this is argmin over expectation of trace of grad x s theta x and plus half of s theta x. Okay, so this is what we proved in the last class, that that computing expectation of this is now same as this. Now if we look into here, then we know that all these quantities are known. Okay, s theta, I mean known in the sense like theta is not known, but then this is something we can compute. Okay, so this is the derivation we did, and then so we did there was a step where we did integration by parts, and then I said that one of the term goes to 0. So that was an exercise. So I hope you can do that. There is a simple trick there, and then when we did this, we were still worried that although we can compute this, unlike this we can still evaluate this, but then there is a problem still, because this is grad of s theta. Now s theta is a d-dimensional function, right? So this is rd. If I take a gradient of this, then it's d by d. Okay, and so computing this is still troublesome because I have to compute the trace. So to compute the trace of this, then I had to take these double derivative terms. So yeah, so so s theta was already for us, its grad x was already there in s theta, right? So this is p theta of x. Now we are having another s theta, another grad x. So like this. So then we have grad x of grad x, okay, and then, or I can write grad xx also. So let us say grad xx, okay, and then p theta log is also there, right? Log of p theta of x. Okay, so this is grad x s theta log, and then I'm supposed to do a trace of this. So this is trace, and this is a trace of this. So the authors noticed that the computing this is expensive because it requires double derivative, and double derivative in the sense that we will do a backprop because this is a neural network here. So in this double derivative, we are supposed to have the trace. I need del s by del x1, okay, squared, and then del s by del xd squared. And there are also other terms, but I'm not worried about that. Only thing I need is the trace, which means that the diagonal entries will be okay. But even to do this, if I have to go to so I have to do this for as many data points as I have, and I have to do it 2 times because it's a double derivative. Okay, so first I have to compute the del by del s by del x 1, and then do it again. Okay, so the back propagation will happen like this for each data points, right? And then all the whatever the dependencies they may have. Okay, and then I have to repeat this one more time to take a derivative again of these. Okay, so to reduce the complexity of these, because I have to do this for d data points, backprop 2 times. Okay, because these diagonal entries correspond to the d data points I have, and these so these d data points are coming. I mean, here these x will happen for component wise. So x is d-dimensional. So first derivative will involve del s by del x1, del x2, del xd. Second derivative, again I have to do the same thing again. So this is the complexity we are looking at. So what they did as a next step is that they tried to reduce this problem by projections. Okay, so then they projected this using some random projections. Okay, then the problem will reduce to the dimension where I am going to project. Okay, so in this case v is let us say d-dimensional, then it will become a d-dimensional vector. So what they did as a next step, what was done here as a next step is another theorem, and so if we define L, so we define L theta v as a projection, and this is half of v transpose s theta x as v transpose grad x log of px. So this is the projection we are talking about. We are projecting on v. Okay, we are projecting this on v, and so rather than minimizing this, okay, which is our original loss. I mean, the very original one is I mean this we got after the. Okay, that's what I was thinking. Okay, so this is this, and then we are saying that this objective, I will reduce it to 1 dimensional. So if I multiply by v transpose here, okay. In fact, in this case, it will become a number because this is Rd, and I am multiplying by v, which is Rd. So it will become an inner product. This will be a number. This will be a number. Okay. So that will simplify. But then you will ask what we will lose information, right? Because if I'm projecting on v, then I'm losing a lot of information, right? So that's so but then to resolve this, there was further theorem that doing this is okay. You may not lose much. So, but before this, what we can say is that what is the minimum of this now, the projected one. So argmin theta, expectation of L theta v is argmin theta, expectation over v from R, x from P, and then this is v transpose grad x s theta x v plus half of v transpose s theta x squared. So this was a result that was also proved in the last class, that this if I change the minimization with this projection, then if I want to minimize this, then it will look like this. Okay, and then the idea here is that this is cheaper than computing this trace of grad xx, because there we only need a Hessian vector product. Okay, it may not be very trivial for you to see why, because you will say that here also I needed to compute the Hessian, and let's say only the diagonal terms, but there also I have grad x s theta, right? So this dxx term was here, but there also I have dxx term here, because this is also grad xx log of p theta x. So how did it reduce? How did it help us be cheaper than this, right? That's a valid question, right? Why that should be cheaper than this? Right? That's a numerical type thing, right? That may not come from theory. I mean, if you see explicitly that both need the same work of computing the double derivative, then why should one be cheaper than the other, right? So the idea comes more from the algorithm here. Okay, how you think about the algorithm. Okay, how you do the backprop, and on what quantity you are computing the backprop. Okay, so the simple intuition behind this is that here if I have grad x and then yeah, so grad x, and let us say grad x log of p theta x and v, and then there is a v transpose. So we have to look into this like this, like iterated, taking this gradients iteratively, right? So the first backprop that I will do will be on this, right? So if I do one backprop, I multiply this with v. Okay, so this gradient then it becomes a number, and then I do a backprop on a number, and then I reduce this again with v. Okay, so then the fact that I reduce it to a number, that makes it lesser complexity than this. Okay, because there I exploit the fact that there is a product with a vector. Okay, so overall this second formulation will reduce the complexity, but there is a catch here, that it is being projected on v, and you have to calculate this expectation over v. Okay, so those expectations which will be kind of an average, right? So what I'm trying to say is, just one vector, choosing arbitrary one vector may not be enough. Okay, so you may have to compute these expectations over multiple v vector. V is like some random vector here. Again, it depends what would be the choice of your v, right? That itself could be a nice research problem here. So you are sampling this v, which is a random vector, but from which distribution you are sampling. Okay, in fact, some people are working on this as well. Okay, what are the good ways to sample v as a research problem? Okay, so but as I said, picking just one is not, may not give you a good idea, right? So we may have to pick many of them, but then those many should not be in a way that it will exceed this double derivative calculations here. Okay, where you have to do this backprop multiple times. Okay, so this is kind of like order d algorithm. This is order 1 algorithm, but if v are taken d times, then it may become same complexity. Okay, so these are the algorithmic choices one has to make. So choices of v is a research problem, but there is a result that this new objective that we have, the theta that we will get from here, this theta will be the one that will minimize the original objective. Okay, so that gives you a guarantee that although I have projected and I'm so working on a projected problem which seems like an approximation, but this result says that the theta star that you are getting from here, if there is a theta star for which that is 0, then that's the same theta star for which the original objective is 0. Okay, so that's a guarantee that that you have. So working with that makes sense. Okay, so theta star that I will get will be a good one. Okay, so do this small proof of why the theta star is getting theta star from here is as good as this, and then I will stop. So it's like 5 lines proof, I think. Okay, so let us try to do this. This theorem is proposition, and this is from the paper by Song and 2019. And suppose Px is P theta star x. Okay, so let us say Px can be obtained via minimizing this this objective for which this theta star there exists a theta star for which P theta will achieve the true distribution. Let us say if our model is like that, then if R is positive definite R is a vector, so but positive definiteness here means that we define it that expectation of V transpose is greater than 0, and V is taken from the distribution R. So that's how we define if R is positive definite, then any samples I take, expectation of V transpose is greater than 0. Then this result says that expectation of V taken from R, L theta V, is 0 if and only if theta is theta star. Okay, so this is good because we are working with that L theta V, the projected problem, and this is 0 if and only if theta is theta star. So that's good. If this is 0, then I know that theta that I used to minimize this projected problem is the actual theta star that I wanted. And if there is a theta star, then other way is also true. For theta star it definitely becomes 0. So this is a nice result. So then so the converse is clearly true. Okay, yeah, I mean, let us put it this way. Let us assume that this is 0, then we prove that this is 0. Okay, and this we believe is the actual loss function, right? If that loss becomes 0 implies this becomes 0, we are done. Okay, so that's the plan. So assume that suppose expectation of L theta V is 0 and V from R, then we have 0 equals expectation of, we put that objective here, V transpose S theta x minus V transpose grad x log px, and then square of that. Log px, and then square of that. This is V transpose, and this is squared, right? So we are assuming that that loss is 0, and we prove that this loss will be 0. So then this is equal to expectation of V taken from R half, and then okay, so we can rewrite this as V transpose S theta x minus grad x log px, and then S theta x minus grad x log px transpose V. Okay, so this square we can write it like this. You can check this. Okay, this is a simple calculation. So so this is true, and then this is, take the half out, and we put the V transpose and V in the middle because that was given to be positive definite. So we will exploit that fact, and that is positive definite, and this V theta S transpose another S theta, I mean S theta minus grad x and S theta minus grad x, they will make a norm, and norm 0 means the inner one is 0, and this will be 0. Okay, that's the plan. So then we make V go in the middle. So you can like do this. Okay, these are simple things. So S theta x minus grad x log px transpose, and this becomes expectation of V transpose. because the random variable only is v, so expectation just goes there, and then the remaining is again s theta x minus grad x log px, and then this guy is positive definite. Okay, so then this guy is positive definite, so only way this will be 0 is when the norm I can remove that basically. Okay, so divide both sides by expectation of VB transpose, and then what I'm left with is this norm quantity here. So this is equal to half of norm of s theta x minus grad x log of px. Okay, so basically divide by expectation of VV transpose, and this is 0. Okay, and this implies that s theta x is equal to grad x log px. Okay, so we have proved that this objective, which is called sliced score matching. Okay, so there is a paper sliced score matching. So this is coming from there. This is called sliced because you are doing it on slices, like on the projected ones. So some of the ideas we take from here is that sometimes you will have a problem which will be high dimensional computationally. So these are the tricks you may do, that you reduce your problem to some lower dimensional stuff like that. Use some randomization. This is a randomized projection technique, right? So look, obviously we are taking expectation, right? So there are a few things hidden here, that I'm thinking of expectations when I am kind of so this is like a on average result, right? So expectation here means that on average if v is taken like that, but it's not specific, right? If I take one vector v, it's not necessary that the projected one will match this. So the point here I want to make is that you may want to do this average over multiple vectors maybe. Okay, rather than just one. Okay, I have not run this code yet myself, so I don't know in practice how many of these projections will be done. So that's something like you can explore for yourself, what they will do in practice, whether they will go with 10 or just one is working okay for them, I don't know. Okay, so this is something we have to check. We can stop, right? So I hope it has given you overview today, because it was a very lengthy topic. There is a little bit of part left. I will take maybe 15 minutes or so on. So the next idea is like sometimes we don't just generate images, but we generate it as a conditional. So I may want to do a super resolution of the images. Then the low resolution will be the condition that I will give. And then sometimes I will put a text and then say create an image corresponding to the text. So then the model and everything remains the same. It's just that now I will have additional conditions given there. So this I will take maybe half an hour in the next class. And this is what DALI and all these are doing. They take a condition on the text and then they generate images. Okay, the condition could be low resolution image and then make it high resolution. So we will look into this. These are not very like intense topics. These are just simple tweaks to the existing model. So this can be covered in half an hour in the next class. And then we will go with LLM models, large language models. We will see how we will start with some basic ideas, how next sentence is predicted and so on. Next tokens specifically are predicted. And these are not very maths oriented ideas. These are more of a engineering type thing. So we will look into regressive models. Okay, as a foundation, linear regressive models, then neural regressive models, autoregressive models. Then we will go into, let us say, LSTMs. Then we will look into first we will look into RNN. Then we will look into LSTM. Then we will look into transformers. Okay, so the basic idea of ChatGPT is very simple. Okay, use transformers to do next word prediction. Okay, so there won't be too much maths in the remaining classes. Okay, thank you.